And we are live. Hi, everyone. Welcome to the Importance of High Voltage Safety webinar hosted by TÜV SÜD Academy. My name is Brad Fernald, and I'm an Academy Advisor for the transportation industry. A little bit about TÜV SÜD Academy. We are one of the leading global providers of professional training and development. With over 150 years of experience, we provide effective training programs for individuals or organizations to support you in becoming an expert in your industry, from work safety management systems and technical skills to high-level executive programs. Our speaker today is Andrew Olson, who has years of experience in electrical safety, batteries, and diagnostics. Andrew founded Electrain in 2017 and has provided instruction and consultation since 2014. He is a certified electrical safety compliance professional through the NFPA and has presented his work in electrical safety at various forums. Currently, he is the president of Electrain and supports TÜV SÜD with electric vehicle and high voltage battery training. Quick reminder to our audience that we have a survey and we would love for your input and feedback so we can keep creating and delivering relevant webinars for you and your teams. And you can find it at the bottom of your screen. It looks like a little notepad. With that said, let's get started. Andrew?
All right. Thank you very much, Brad. Here's a little bit, I guess, about TÜV SÜD. As far as just a little bit of the background here, there's going to be a link. You can see that there's a link here on the screen as well for you if you guys have any follow-up questions, but we'll have a QR code that'll take you there towards the end of the session. So with that, let's go ahead and continue on. Today, we're going to do, we have just a little bit of time, and there's so much information to talk about on this subject. So, and there's a lot of questions whenever we get out into the industry. So I'm going to try to do a little bit of an introduction to what are some of the technologies that we're dealing with, what are the challenges, what are the things that we have to understand in order to work safely with this technology, and then what are some of the training solutions, which is ultimately what we're going to get to. So our first objective here, we're going to do an overview of high voltage batteries, and we're going to kind of tie in a little bit more about electric vehicle applications here because that is a big part of the market. But if you don't work with electric vehicles directly, if you work with the testing or the production of high voltage batteries, then stick with me here because the rest of this is going to be just as applicable. We're going to go into an overview of electrical hazards associated with the high voltage batteries. And sometimes this is a unique first time experience for somebody who's been working with, especially with automotive for their careers. We're going to do a review of risk assessment versus hazard assessment, and specifically focused on high voltage DC applications. And then we're going to identify high voltage battery PPE and controls that we have to consider for implementation. Now, obviously, in our brief meeting here today, we're not going to be able to give you guys all of the direction on how that works, but we'll introduce what are some of the concepts we have to be familiar with and why they're important. And then towards the end here, we're going to kind of wrap up with an overview of the training requirements and the levels of certification that you need to consider if you work with these types of hazards. So with that, we're going to kind of start off with just a rough block diagram of what an electric vehicle kind of looks like. Now we start off with an AC power supply. As you guys can see here, this AC power supply would also be known as a charging port, right? Which is going to go through some sort of a rectifier circuit, typically referred to as an onboard charger. So that onboard charger is going to convert our AC to DC, or it's going to recognize that we're doing a DC fast charge, and it's going to provide that power to ultimately to our battery. And that can go directly to our battery. It could go through a power distribution unit. It could be some component like a penthouse, as we see on like the Tesla Model 3s or something like that, that's going to just direct that power to where it needs to go. From there, we're going to have other high voltage components that are pretty typical in every other electric vehicle application, which is going to be three-phase motors. And typically we're using three-phase motors, although we're seeing some members of the industry get kind of more adventurous and experiment with like six-phase motors, which we're able to now start to utilize because our inverters have the technology for us to be able to do so. And those will give us some additional advantages as well. So we have AC, basically AC motors that we're utilizing to drive our wheels or to provide power to our AC compressor or other high voltage loads, depending on the application. So we need to have some sort of an inverter that's going to provide that power. Likewise, this inverter has a function of being able to reclaim energy, especially if it's a drive motor. So it's going to be able to convert any generated AC from our braking motion or anything like that back into DC so that it can, resupply the battery. Other typical high voltage loads would include our high voltage heaters, as well as our DC to DC converter. And so this DC to DC converter has a lot of functions in it as well. It's going to supply our low voltage system, but it's also going to provide for us what we refer to here as galvanic separation, which is going to make sure that the low voltage negative terminal tied to chassis does not conduct through that circuit back to our high voltage side. But one of the basic principles for safety in high voltage electric vehicles is that the positive and negative bus are both completely isolated from the chassis. We don't want that tie to conduct backwards through there, so that DC to DC converter is very important for us, that it's designed to prevent that tie to chassis from going from the low voltage circuit back to the high voltage circuit. So those are the basic components. We really don't have a whole lot of high voltage components whenever we look at this. It's pretty standard, pretty simple. The arrangement can look completely different based on what platform you're looking at, but we all typically have the same basic functions. And so as I go through here, I got a couple just pictures just to demonstrate what some of those components might look like. Here you're taking a look at the top of a battery. This is a battery assembly, high voltage battery that has the cover removed, and you're looking inside and you can see that there are modules on the left-hand side here. There's 8 separate modules included inside this battery. They're all connected together to give you an overall high voltage battery power. We have our contacts here at the output, as well as a fuse, and we have our heating and cooling lines coming in to maintain temperature of that battery. So all of this is contained inside that battery enclosure. And on the right-hand side, you can see one of those modules, the cover removed. We can see that there's wiring internally for our battery management system, as well as some of the individual cells. Now, this kind of comes into play later when we talk about risk versus hazard. Here you can see this is the first point in time where we've actually exposed on this particular battery any exposed energized conductors. And we can see that here at the top on the right-hand side in our module. Whereas on our left-hand side, when we removed the cover, everything that was energized was still covered up. So this all comes into play with our risk assessment. And when you're looking at how risk applies to you and your team, it's going to drastically depend on the design of the equipment that you're working with. Inside high voltage vehicles, anything that meets their definition for high voltage, which is going to be greater than 30 volts AC or greater than 60 volts DC, is required to have its cabling annotated by orange insulation. So you can see, looking inside this frunk of a vehicle on the left-hand side, that we have an orange cable, which is actually going to an AC compressor. That's a high voltage cable, so it has to be colored in orange. And that's what you see on the right-hand side here with these cables as well. Typically, our high voltage cables are going to be shielded, which is going to prevent our system from having any kind of challenges from electromagnetic interference, as well as from sending out any kind of electromagnetic waves or interference that might potentially cause induction in the vehicle. We have connectors that are going to be rated what we call IP2X, which is a touch-safe connector. What that means is when this connector is disconnected, I can't stick my finger inside that connector and touch an energized part. It's going to be safe enough to prevent me from being able to do so. And so we have this level of engineering throughout our vehicles as well, which drastically helps make sure that we maintain a safe environment. Here's another couple connectors. We can see additional safety features. You can see on the surface here of our connector that there's little key marks, which helps prevent you from putting it in backwards, where you might inadvertently reverse polarity, which could be a problem when you're connecting a connector. So that's one of the safety features that we typically see. There's another, it might be kind of hard to see on the right-hand side here, a safety circuit we refer to as HVIL, which is something that we go into a lot more detail whenever we get into like our classes. But that's a safety circuit that's important to understand. And again, we have that IP2X rating, where even on this large conductor on the left-hand side, there's an insulated barrel in the middle to prevent me from, of course, trying to stick my finger in there, right? So it's going to keep us safe. On the left-hand side, we can see some motors that are basically built right, and these are driving the wheels directly. So this is a tandem axle here where we have two motors, one on each side, and those have the inverters built right into them. So they have power coming right up, and then the inverter's built right onto the top of the motor, and then you have power directly to your wheel. On the right-hand side, we see another example of an inverter, and we can tell this is an inverter. If you were to count these orange conductors, we have two oranges that are going to be our positive and negative, and then the other three orange wires are going to be our three-phase AC that goes out to our electric motor. And then I mentioned another component, which was a power distribution unit. And this is typically going to be what's at the output of your battery. And this is going to be a point where we can have high voltage fuses outside of the battery enclosure to the other high voltage loads. That way we have selective protection. If there's a fault with one of our motors or something, it'll only take out the fuse that goes to that motor rather than taking out our entire high voltage system. So these are typically going to be utilized as well. You see these more accessible and more often used on industrial type equipment. And then we have, in addition to the orange insulation, typically we have markings outside of our high voltage compartment. So you can see both pictures here, that little orange triangle with that lightning bolt on it to indicate that there's a shock hazard, there's a high voltage hazard inside of those enclosures. So in order to open that up, you have to be a qualified person to do so. Now, lithium-ion batteries, and really all high voltage batteries, whether you're dealing with lithium-ion or sodium-ion or anything like that, they're going to come in three typical form factors. And the first one is cylindrical. Cylindrical is kind of more like a AA battery. It's a smaller size. They do get larger than AA batteries, but still typically the smaller form factor for our high voltage batteries. And these ones are kind of made more famous in application through companies like Tesla. They use a lot of cylindrical cells in their manufacturing, which requires, since they're the smallest, it requires a lot of them in parallel to be able to supply a significant amount of current. So we typically see lots of these being used in those applications. The other two main form factors that we see are pouch cells, which we see here on the left. They are kind of the least expensive to manufacture, and they also provide a lot more current capacity. So we see a lot of companies that are currently using pouch cells for those reasons. And then the last one here is prismatic cells on the right-hand side. They usually have the highest current capacity, but they are typically more expensive. They also have more protective features built into them, which is also part of the reason why they are more expensive. So it's a good balance between safety as well as being able to supply a tremendous amount of power. So those are the three major form factors that we typically see in our industry. Currently, in North America, we're kind of lacking a really good guidance for how to deal with our safety when it comes to high voltage batteries. And I know that for a lot of you that are currently attending, that's probably one of the biggest things you're concerned about. What we currently have on the market, or not really on the market, but in the industry providing guidance, is we have OSHA 29 CFR 1910 subpart S. That's general industry standard, has basic electrical safety requirements and not really written for application for electric vehicles. We have NFPA 70E, which many of you may be familiar with, which is also the standard for electrical safety in the workplace. It really gives a deep dive into electrical safety in pretty much every application, but it excludes a few things, one of them being for vehicles, right? So it's not really part of the scope, and it's written to address much more complicated and difficult electrical hazards. So it does not really line up directly to provide the best guidance for us. Although we can take a lot of good stuff away from there and use it in application for us in North America, which is currently one of the best practices for us to do. We have the Federal Motor Vehicle Safety Standard, which provides a lot of requirements for us. It's a design requirement. That tells us that we have to have like the IP2X connectors. We have to have the orange insulation. We have to have isolation of our high voltage buses from our chassis. All those things are included in the Federal Motor Vehicle Safety Standard. And then for our neighbors up in Canada, we have CSA Z462, which is basically a duplication of NFPA 70E, except it's for Canada. So where are they going with our standards currently? Right now, I'm currently working with the CSA Z462 committee to write an addendum to go to the end of that that's going to provide guidance for electric vehicle safety. So there is going to be an addendum to Z462 in Canada, and that will be coming out in the next, hopefully, couple of years. And then we have, for the United States, IEEE has just commissioned a working group to provide a electrical safety guidance for North America for electric vehicles. So we have two different standards currently being worked on for scope within North America. So we'll see more to come here in the next year or so. All right, so that's kind of an overview of the technology and where we're at so far. So what are the hazards that we have to be concerned with when it comes to electric vehicles or to high voltage batteries? I'm not going to be able to go into super depth on this because this topic alone will take several hours just to go through the physics of what goes on with each of these items. But to kind of give you a main introduction here, there's 4 electrical hazards that are identified in NFPA 70E. It would be thermal hazard, shock hazard, arc flash hazard like we see here, and then lastly they touch on arc blast hazard. Arc blast is not something that we have to be concerned with within our high voltage batteries unless we're working with extremely high energy capacitors. So that's typically, even though we have capacitors for power conversion, we typically don't get into that level of capacitance. So these 3 are the ones that we want to focus most of our time on. A thermal hazard is something that we've seen in the automotive industry for a long time. This is where you might have a 12-volt battery, and many of us have done this, where we go up and we've touched both terminals, the positive and negative, at the same time, and we don't receive a fatal electric shock, not even a hazardous electric shock, right? So it's not to the threshold where we can receive an electric shock, but if we were to take a screwdriver and touch it across the top of those terminals, we're going to see a lot of sparks. We're going to see even possibly a blue arc there, and there's going to be a lot of heat that's released that could cause first or second degree burns to our hands, right? So there's a lot of heat there, thermal energy, but it's not quite to the level where it's a shock hazard or even close to being an arc flash hazard. A shock hazard comes into play with, depending on which standard we're going with. If we're in Canada, we consider it whenever we exceed 30 volts AC, 60 volts DC, we're calling it a shock hazard. Same thing with our friends in Europe. In the United States, we go with 50 volts. If we're complying with OSHA, they say 50 volts for everything, whether it's AC or DC. And then if we look at NFPA 70E, which is one of the most up-to-date standards because of the research that's constantly going on, they recognize that 50 volts AC is a shock hazard and 100 volts DC being our level for shock hazard for batteries. So you kind of have to assess where you're at, what are the standards that apply, and what are you guys able to legally take liability for, and then establish your threshold at your own facility. I'll just provide guidance as to where to go and which one to refer to. But that shock hazard, if we exceed that, is going to provide enough voltage to break down the resistance potentially of our skin and be able to provide enough current through vital parts of our body, such as our heart or our brain, and be able to provide a fatal shock. So if we're getting into those thresholds, we obviously have to start considering using additional PPE. PPE being personal protective equipment, and in this case, we would use, in North America, rubber insulating gloves with leather protectors. If you were in another continent, they might just tell you to use rubber insulating gloves. North America, anytime we're using rubber insulating gloves, we always have to have the leather protectors to go along with them. So we want to make sure we're reinforcing the best practices here in North America and not just adopting half of the practices from other continents. Lastly, we have the arc flash hazard. This is a much more dramatic hazard that is something that we've typically just seen in three-phase like facilities. So industrial applications, the average person who just does the work at their own home and stuff has never been exposed to this until now. So arc flash hazard for DC becomes a concern anytime we exceed 150 volts. So if we have any kind of high voltage battery system or any part of that system that is exceeding 150 volts, we have to evaluate that arc flash hazard, take into account what the protective devices are, and then we can calculate how much heat energy can be expelled from that in the case of a short or an arc flash occurring. And if that occurs, that heat isn't going to just be at a distance, kind of like when we were shorting out the battery with our screwdriver. That heat is going to expand out in a plasma cloud, and it's going to touch our face and chest and possibly envelop us and cause immediate third-degree burns. This is a whole different type of hazard that we have to make sure that we are being mindful of and not taking for granted, right? And I've seen a lot of the industry just prescribe, we'll put people in category 2 PPE, they'll be fine. That's a good practice. It's not a good practice unless you actually evaluated for it. We can't just assume things, right? We all know it happens when we do that. So there's a lot that goes into these hazards. Those are the three main ones, but it's kind of a brief overview. Hopefully you kind of answered some questions for you on those, probably developed a few more for you, but that's a big thing that we need to focus on whenever we're dealing with high voltage battery systems. So what is a risk assessment versus a hazard assessment? A hazard assessment is when we take a look at something that's actually providing a hazardous environment to us. Like it's something that can actually release energy. And in our case, we're concerned about the battery itself, right? So that would be our hazard. Risk is how are we interacting with that hazard, and is there going to be any kind of risk to the person based on that interaction? So for a hazard assessment, we can analyze that just by taking a look at the specs of that system. So we're going to look at we can quantify it, and we can say, does it exceed the high voltage threshold, 30 volts AC, 60 volts DC? If it does, if we're exceeding that level, then we have to have a qualified worker to be able to do that task. We can't just have any random person doing it. They have to be trained and qualified if they're working above 30 volts AC, 60 volts DC, specifically on like an electric vehicle system. If it's greater than our shock hazard threshold, which could be 50 volts or 100 volts, depending on what you're applying there for DC, then we have to have the proper PPE for that shock hazard, which is going to be our voltage-rated gloves and leather protectors. And then if we exceed that 150 volts, we have to perform our arc flash assessment, and then in turn, wear the appropriate arc-rated PPE, which we'll cover here in a second. So we can quantify it based on those things. And if we were doing an arc flash assessment, the things that we'd have to know are what are the internal resistance of a cell, and if we knew that, we'd have to know what the configuration of the battery is. How many series cells are there connected together, and how many are connected in parallel? And if we do that, we can mathematically determine the total resistance of the battery, the total, the total voltage of the battery, the maximum shorting current of that battery, and then we just need to know what is the protective device that's in that series, and if there is one. If there is a protective device like a fuse, we can then take a look at the ratings of the fuse and determine how fast it'll trip if there was a worst case scenario, and then we can get our calculation. So there's a lot of things for us to evaluate, but it's really not super difficult. It's pretty easy, but that's one of the things that we definitely help you be able to do. So for risk assessment, we want to take a look at what is the likelihood of occurrence versus the severity of the incident. If we're dealing with some of our higher energy batteries, we have batteries right now in the market that are as high as 1,500 volts in both energy storage system applications as well as electric vehicle applications. So we're hitting the top of that threshold right now in both sides of the industry. So that could be a tremendous amount of severity if something was to go wrong. So we have to take a look at what we're doing and what is the likelihood of something bad happening. And then we can take into account how we're interacting with that equipment and determine, based on that interaction, do we need additional PPE or any other safety practices in order to do that work? Let's just say, for instance, we have a high energy battery that's sitting in the bottom of a vehicle that we're going to be driving. That has a high hazard, but it's enclosed, it's insulated. We have monitoring systems that are making sure that everything's okay, and we're not intruding onto any energized components. So do we need to wear any additional PPE to drive that vehicle or need any additional training? No, we do not. But as soon as we start to do maintenance on that system, where we might break that threshold where we're exposing energized conductors, now we need to have training, and now we need to possibly be implementing PPE depending on the state of that system. Some of the elements of a risk assessment procedure would be identifying the hazards. And this is really kind of directives from NFPA 70E specifically. We need to assess the risks, implement risk controls according to the hierarchy of risk control methods, validate the effectiveness of risk control measures taken, and then document. So this is one of the things that I see a lot of employers currently missing right now is proper documentation of your risk assessment. This should be done through an electrical safety program, which for a lot of people in this industry is a whole new concept. But you're dealing with energy, electrical energy. An electrical safety program is not very far off to think that you might need to have, right? So there are guidelines for that in NFPA 70E. If you're not familiar with it, I recommend you check it out. Otherwise, plug into some of the training that we have here, and we'll definitely help you out with that as well. Now, this talks about the hierarchy of risk controls. I'm not going to cover it in detail, but this is kind of an example of what it looks like. You may have seen the same thing flipped upside down. It doesn't matter. It's usually set up as a triangle. But what it is telling us is that the most effective means of keeping somebody safe is at the top. And the most effective thing we can do is eliminate that hazard. In electrical safety, that means that we turn off the electrical power, we lock it out. So now we have to apply lockout, tag out, which is sometimes new for us in this industry. And then we have to verify that it's de-energized. With us in North America, that means we're getting a meter. We're going to take that meter, we're going to check it on a live circuit to make sure that it's working properly. We're going to verify our de-energized circuit is de-energized, and then take that meter and check it on a live circuit again to make sure it's still working properly before we can say for sure that that system is safe for us to touch without PPE. Other continents have different ways of assessing that it is safe. Here in North America, that is currently our best practice and our accepted standard. So that's our preference here for is elimination, substitution, engineering controls. Those are also good things to do. We incorporate lots of engineering controls in our systems like that IP2X connectors. Awareness would be like the orange conductors or the labels on the outside of the high voltage enclosures. Administrative controls would be lockout, tag out. It would be your training requirements, and then PPE being your last least effective measure, right? And we say that's the least effective because at this point in time, we're just slapping gloves on you, putting on some clothes that'll hopefully protect you in case there's an arc flash, and then putting you right next to the hazard. So we're taking a little bit more liability there. It's a little bit more risky. We don't want to count on that first. We want to do everything else we can to keep the hazard away from you before that. Excuse me. So here we have an electric vehicle risk assessment. This is just an example of how you can document that hazard. If you guys are dealing with the same battery day in and day out on different vehicles, then you only have to do this once, and you just document what is the task you're doing. Are you using lockout, tag out? What is the arc flash hazard? What is the shock hazard? And what PPE is required? It's a pretty straightforward, simple form to fill out, easy for you to develop for yourselves. We always have to account for human error as well. And this was a big thing that was emphasized in NFPA 70E, is that we're going to make mistakes. And it's to the point where it's predictable. So if we have a significant task that has to occur, that if we do it wrong, it's going to cause injury to a person or to the equipment, then we can take additional steps and precautions to help minimize the chance of human error occurring. And that would be stuff like having written work instructions, performing a pre-job brief, or having a second person there to validate that we're doing the right steps. So those are easy things for us to incorporate, make sure that we have as part of our processes. So high voltage battery, PPE, and controls. First of all, we have to start taking into account boundaries. These boundaries are protective boundaries based on the hazards that we're exposed to. And this can be a lot to digest, and is typically one of the more challenging things for us to try to instruct with people who have never been exposed to this before. So if we have a high voltage hazard, and that high voltage hazard has an arc flash hazard along with it, meaning that we have a heat energy that's exceeding 1.2 calories per centimeter squared, that means we have to establish an arc flash boundary. 1.2 calories per centimeter squared is the amount of heat energy that we would receive that would start to give us second-degree burns. So if we're going to cross this boundary, this arc flash boundary, we would need to have covering our skin, all exposed skin, and all exposed non-rated like shirt and other apparel, that would all have to be covered by ARC rated PPE. So that would typically mean we'd have to have coveralls, we'd have to have leather boots, our rubber gloves with leather protectors would protect our hands sufficiently. And then for our face, we'd have to have a balaclava, which would be a sock hood that covers our whole face and back of our head, and then an arc flash face shield, as well as safety glasses underneath, hearing protection as well. So there's a ton of PPE we'd have to make sure we have on to cross this boundary in order to keep us safe in case something went wrong. Now this boundary, to be honest, in most cases is with the amount of protection we have in a lot of our high voltage systems, is that threshold is that amount of energy that is released is so small, this boundary can sometimes be the closest boundary. So it's a dashed line because it's variable. In a lot of cases, it's going to be inside of this restricted approach boundary, and we don't even have to have additional controls. But that's why we have to evaluate. We have to do a calculation and verify that. We don't want to make assumptions. I was just working with a company the other day that is manufacturing batteries, and they don't have protection built into their system at the level that they're having workers work with these modules. And they found out that they have a significantly high, I'll just say in the ballpark of like 18 calories that they are exposing their workers to, and they don't have PPE for that currently. So this is why we don't want to just assume that category 2, which if you're familiar with category 2, that is rated for 8 calories, category 2 will protect us, because in that particular example, they far exceeded category 2 and they didn't even know it. So we have to do these calculations to verify that we're safe, and then establish the boundaries to keep other people safe. A limited approach boundary is just a shock protection boundary. It's basically, if you have exposed energized conductors, metal looks like metal whether it's energized or not. So if you didn't know anything about the system, you wouldn't know that that was a hazard. To keep people who are unqualified safe, we put up a boundary so that they don't accidentally go in there and touch something that's energized. That's all this is for. Our working distance is where we calculate our incident energy, which we'll go into more detail inside of a class. And then our restricted approach boundary, if we cross this boundary, we basically assume that because we're talking with our hands or whatever, that we're getting close enough that we'll inadvertently come into contact with that energized conductor. So to cross that restricted approach boundary, we have to have rubber gloves and leather protectors. So these boundaries each have their own special purpose. They're important to understand, and that's one of the biggest things to walk away with when learning about the high energies of battery systems. Whenever we're directed to wear arc-rated PPE, I listed off all the things you need to have, like you said, long sleeve shirt or pants or coverall, or an arc flash suit. You have to have a face shield and balaclava, or an arc flash hood. We have to have, if you have any outerwear, it needs to be arc rated as well. Rubber insulating gloves with leather protectors, hard hat, safety glasses, hearing protection, and leather footwear. And that's for up to 12 calories of exposure. If we exceed 12 calories of exposure, the only thing that changes is we can't use a face shield and balaclava anymore. We have to use a hood, because when we get above 12 calories, the energy is enough that it could wrap around underneath the face shield and burn the little bit of exposed skin that we have that's not protected by the balaclava. So we have to transition to a full hood at that point in time. As I said, for anything that's greater than 150 volts DC, we have to do an arc flash calculation. There are several calculators out there that we can direct you to that will help out with this. Or if you guys just want to do it yourself, we can show you where the equation can be found, and you can sit there and type it out on your calculator yourself. But some of these Excel calculators make things a lot easier. It's not super difficult. It's pretty easy to quantify. The hardest thing, honestly, is trying to find out from the manufacturer what the internal resistance of the cell is and what the fuse was that was put into that for overcurrent protection. If you can find those two things, this is going to be a piece of cake. So we have to incorporate several different safe electrical work practices as a result of these higher voltages and these additional hazards that we're going to be presented with. So we have to think about identifying our boundaries that need to be established, as we saw before, and actually put up physical boundaries to keep people out. And we want to make sure that these boundaries aren't the same thing that we use for everything else. I got to say, one of my customers had incorporated boundaries where they just used little traffic cones that they wanted to use to put up around the work. And then when he took a look around the rest of the shop, traffic cones were being used everywhere. So it wasn't unique to this hazard. And people were already kind of numb to the application of these traffic cones because they're all work there, so they're authorized to walk across them. This needs to be something that is unique to this electrical hazard so that people stop and recognize that maybe they should ask before they cross this boundary. We need to identify the required PPE in order to do this work. We want to make sure we're utilizing insulated tools. We want to plan the activity to minimize exposure. And this is really a key component. And until you actually stand there in the PPE yourself with all the things in mind that you have to do, and then find out that, oh, wait, we have to brief still, or we haven't checked our meter yet, or we haven't inspected our gloves, and you're sitting there in all the rest of the PPE, and you're just sweating and getting clammy. You're having a hard time hearing inside of the hood and the hearing protection. You want to make sure you plan accordingly so you minimize how much time you're in that PPE and that you're minimizing your exposure. You don't want to go in and just take the cover off and then do all the work with the entire battery exposed, when maybe you could reduce the risk by putting insulating blankets over a majority except for the area that you're working at. So there's things that we can do to minimize your exposure to the hazard as well as minimize your time in the PPE. Both of those are extremely important. So this is something that's, once you've done it a couple times, you realize how important that is. Inspect your PPE, your tools, and your instruments prior to entering the boundaries. So that way you're not going in and out. And again, just lengthening how much time you're inside of all your PPE. And then your pre-job brief, you want to make sure you do a pre-job brief, which would include where is the location of safety equipment, including an AED. What are your PPE requirements? Make sure everybody understands what the requirements are, especially for different phases of the work. Understand what your electrical hazards are. What are the steps that you have to do, and what are each person's responsibilities within those work steps? And then when can the boundaries and the PPE be relaxed? Because once you're dressed up in it, that's a pretty important question you want to make sure everybody's on the same page with. All right, so that was a pretty broad overview of some of our hazards, some of our work practices, as well as some of the applications within the industry. So I'm going to kind of take you on what are the recommended best practice trainings that we can do here in North America currently. And we have right now kind of 3 different levels of training. And this is based off of the same training levels that are in place in Europe, which those are required by standards governed over there. And the best practice is really being applied here. And we see this being used by many training entities, including ASE for mechanics. So we see level 1, 2 primarily being done. TÜV Süd is one of the very few that are actually training level 3 as well. So level 1 training is basically a fundamental awareness training for electric vehicles or for batteries. It's going to cover the basic hazards. What are they? Why you want to stay away? Why you need to be qualified if you're going to do work inside of there. So you understand what you are authorized to do, and you know the boundary to where you need additional training and qualification before you can perform that task. This would be for somebody who's doing work on the vehicle, like maybe if they're moving the vehicle around within the shop, if they're changing tires, if they're replacing fluids, that kind of stuff. Level 2 is where we're now starting to interface with the high voltage system, but we're doing it in a de-energized state. So this is going to be where we are authorized to verify that the vehicle is de-energized. So we're going to do that whole establish an electrically safe work condition. We're going to turn it off, lock it out. We're going to use a meter to verify it's de-energized. But we have to assume it's energized until we verify it's de-energized, which means you're going to have to be trained on how to use the proper PPE, establish all the boundaries, and treat it like it's energized. So we're going to be going through and doing that, making sure it's de-energized. And once it's de-energized, we're basically taking on that liability, that safety, to make sure that everybody else is able to do that work. And then we can do things like a motor replacement. If we need to replace an electric motor or an inverter or a heater or something like that, any of those high voltage components, we can now work with and replace in a de-energized state. Level 3 is the highest level of qualification that we have, and that is for work on energized systems. So this would apply to battery manufacturing or to battery testing facilities, but it also applies in the automotive industry as far as if we have, for instance, a loss of isolation, which means that the chassis is now energized at bus potential. We would want to have level 3 qualified people do that work. Or if the high voltage contactors are welded shut, which that happens on vehicles, and then we don't have a way of isolating that energy. So the high voltage system is energized. We need to have a level 3 person safely de-energize that system as best as possible and remove that battery. So level 3 is going to be the one that interfaces with high voltage components, including if to the point where we may at some point in time do servicing on individual batteries. I know some manufacturers are designing with that in mind currently, where they might be able to go in at a service center and open up the battery itself and replace individual modules. And if we're doing that, then those workers absolutely need to have level 3 type of training. So those are the 3 levels that we typically see as an industry practice currently. At TÜV Süd, they provide level 1, level 2, and level 3 training. All of that is currently available and something that can easily be scheduled. And in addition to that, they have a safe handling of high voltage batteries course. The safe handling of high voltage batteries is something that can be done remotely online. And this is good for battery manufacturers, battery testing facilities, and EV manufacturers, where you have individuals who are handling the batteries, moving them from point A to point B, whether it's fully enclosed or maybe they're handling low voltage cells before they get up to a high voltage level. And they're not doing the live work. Once you get into live energy work, you obviously start to fall into the level 3 type training. So we have these courses here available. Be glad to answer questions about them. And you guys can explore for yourself. You guys take a second and use your phone to identify that QR code. I would give everybody a second to do that real quick so you guys can find that link. And I'm sure that we can also have put into the chat or something the link as well. So if we can have maybe somebody do that for us, that might help out. And with that, I'm going to leave it here for right now in case you need to access that. But our next slide is just going to ask, do you have any questions? And so I'm going to go ahead and turn it over to Mr. Brad Fernald, and he will help coordinate questions for us.
Excellent. Thank you, Andrew. Thank you for that presentation and your expertise. So we have a couple questions loaded in, so let's get some of those answers. The first one is, how can a Lambda mechanic know when what is the arc flash incident energy of an EV he is working on?
So was that an LMDA? Is that what you said? What kind of mechanic?
Yeah.
LMDA, so it's a racing vehicle, I'm assuming. That one's a little bit difficult because I know that the individual teams themselves don't work with that. So that's something you'd have to work with the racing circuit or with the manufacturer to demand those thresholds. And I'm actually intending to reach out to that racing circuit to ask that they provide those numbers to the teams themselves as well. So I understand that that's a little bit of a challenge. The best thing you can do is ask, what is the incident energy? Because I know that their procedures will prescribe certain levels of PPE. Specifically, this is one of the things in that circuit that I have a disagreement with, is they prescribe a face shield. They don't mention a balaclava or any kind of arc-rated clothing, but they want you to have an arc-rated face shield. None of our safety standards require just a face shield. So that's already kind of an issue there, and that's a problem in this industry. There's just not enough expertise out in the field to necessarily navigate all these challenges. So I know they're trying to do the right thing, but they're kind of falling short there. Not to throw anybody under the bus, but the best thing you can do is request the incident energy, or just continue to request from the manufacturer that internal resistance and the fuse rating.
Excellent. And just a quick follow-up to that as well. What about an average mechanic? How would they know what the arc flash incident energy in an EV could be that they're working on?
Again, that's something that manufacturers, and I know that we probably have some here in this group that have attendees. Manufacturers don't necessarily want to provide that information because they want to minimize people going in intruding on those batteries who aren't qualified by that manufacturer. So they don't make this readily available. I think the industry is going to have to change to require that. It's almost to the level where that should be something that's like on a safety data sheet, because it does affect people downstream, and people, we know, repurpose these batteries later on in life. So I think that we're going to see an industry change where manufacturers are going to be required to give this information. But as of right now, we have to reach out and ask the manufacturers directly. We can't, there's no repository and there's no rule of thumb for us to make assumptions with.
Excellent. Thank you, Andrew. The next question is, where is the training located? Actually, I can field this one. So our high voltage safety trainings are meant to be delivered on site in private sessions for groups of 10. That being said, we do have some exciting updates coming later this year. So stay tuned for that. But with our private sessions, what we do offer, Andrew or one of our other subject matter experts will come on site, deliver the training for you. It's a week long. You work on your tools, your PPE, your equipment. So students going through the session will gain that experience and familiarness to their day-to-day work, and being able to incorporate the things that they learned, the knowledge and the skills in the training, and have them connected to things that they're going to do in their day-to-day tasks. Next question is, when can we expect standards that direct electric vehicle safety work practice in North America?
It's a tricky question. I've been, unfortunately, been saying it could be within a year, but I've been saying it for the last 2 years. And there's been some, again, not to throw anybody under the bus, but there's been some bottlenecks in the industry that have kind of had too much on their plate and kind of prevented this from moving forward. As of 3 weeks ago, IEEE Standards Committee voted to actually start this working group up to draft this standard. And there's a lot of motivation within that group and participants from across the industry that want to see this happen within the year. So we're aiming for within the year. I'm going to say we can expect it within 18 months, give a little bit of leeway, but that should be a standard that is sponsored by, it's an IEEE standard, and the scope should be for all of North America. As I said in the presentation, we also have an amendment to CSA Z462. I don't know what the timeline is going to be for that. They're not beholden to the same three-year periodicity of NFPA, which they kind of closely resemble the NFPA 70E. So Canada may see something. Maybe it's faster, maybe it's 6 months, maybe it's the same timeline, 18 months, but I do know that we're going to be working hand in hand with them to make sure the two standards speak well and hand off between each other.
Excellent. Good. Thank you. All right. So just a reminder, everyone, at the bottom of your screen, you're going to see the little Q&A. So please, if you have any questions, still feel free to ask them. We still got some time to answer more questions if you have them. The next question is, does the battery chemistry make a difference on what type of training that is required?
So that's a good question. There's several different chemistries within the lithium ion by themselves, and then we have sodium ion and even more chemistries that are on the horizon. And to answer that real quickly, it doesn't make a difference as far as the electrical hazards go. We still have shock hazard, we still have arc flash hazard. Sometimes those chemistries do provide some difference with the chances of like thermal runaway occurring. Some of them are more stable than others, but they still provide shock or arc flash. So when it comes to electrical safety training, it's going to be the same for all those chemistries.
Excellent. Another question just came in. When are we going to see standards for high quantity battery / high energy storage rooms themselves in warehouses, service centers, etc.? So
I know that IEEE is also commissioning one for battery energy storage systems, another standard. So there's kind of there's three paralleled standards that are all working simultaneously. One of them's for high voltage battery energy storage systems. The other one is for more unique electrical hazards like capacitors or high frequency drives. And then there's one for electric vehicles. All three of those are working in concurrent timeline, and we should see some additional direction being added to that field by IEEE, probably in the same timeline, about 18 months.
Excellent. All right. I'm checking doing a quick little refresh on my side. Looks like from a question perspective, that might be all that we have in. If you have one on the top of your head, feel free to drop it in now and we can get to it real quickly. But if not, that is about, we're at time for what we have available today. I wanted to thank everyone in attendance for taking the time to be here with us as we deliver this webinar. And I want to thank you, Andrew, for taking the time to lend your expertise and your speciality to this topic. It's an important topic for everyone in the transportation industry as this new technology is evolving and emerging and changing the landscape. Don't forget as well that we do have a survey, and we really appreciate your feedback and ideas to how we can create more relevant webinars to what you'd be interested in to see, what else we can provide you to enhance your overall experience with TÜV SÜD. So that being said, thank you again to everyone who attended. And if you have any questions, please reach out to us at any time. More than happy to help.